Hello, everybody, and welcome to this section 7, the theory and generalization. The second talk this afternoon will be by Professor Weiqiang Wang. My name is Angela Pasquale. I'm honored to be a moderator. I'm a professor at the University of Lorraine in France. So Professor Weiqiang Wang is a Gordon T. Wyborn professor at the University of Virginia. He received a PhD in mathematics at the MIT in 1995, and he was a member of the Institute of Advanced Studies in Princeton. He was a Gibson instructor at Yale University, visiting a Max Planck Institute in Bonn, and assistant professor at North Carolina State University. Later, he moved to the University of Virginia. His research interests are representation theory and the connections with algebraic combinatorics and algebraic geometry. This is a recorded video of the lecture. The lecture took place at the Institute of Mathematical Science in Singapore, but Professor Weiqiang Wang is with us. So at the end of the video, it will be possible to answer questions that you might have put in Discord. So you can send in then a question. So now we are happy to see and very delighted to see the talk. Professor Weiqiang Wang is going to talk about what is an I quantum group and what it is good for. Thank you.
Next speaker, Weiqiang Wang from the University of Virginia, will be talking about, he will convince us that we should all be studying I quantum groups. I personally look forward to that. And he received his PhD in '95 from MIT under the direction of Victor Katz. Since then, he has been a member of the Institute of Advanced Study, Yale, Max Planck Institute. He has been at North Carolina, and he has been at the University of Virginia, and there where he holds the professorship of the Gordon T. Wyborn professor. He has received, in recognition of his accomplishment, he has received the Chevalier Prize in Lie theory. His interest is in representation theory and its connections to algebraic geometry, algebraic combinatorics rather, and algebraic geometry. And he has been a frequent visitor at Academia Sinica in Taipei, as well as ECNU of Shanghai.
Thank you very much for the introduction. And also thanks for coming. It's much more fun to give a talk to a live audience, and thank the organizer for organizing this event. So before I explain what is an I quantum group, let me provide a quick review about quantum group. That was about 3 decades ago. Greenfield and Jimbo invented quantum group. So what is a quantum group? You start with a semi-simple real algebra, such as ACON. You consider its enveloping algebra, U of G. In the category of Hopf algebra, you consider this Q deformation. It leads to the quantum group denoted by UQ of G, or simply just U. There was such a precedent Q deformation known before. If you consider instead the well group, such as symmetric group Sn, its group algebra admits a Q deformation known as Heck algebra. And in this case, you only need to define the quadratic relation, Hi plus Q inverse times Hi minus Q equal to 0. In the Q goes to 1 limit, you recover the simple reflection from the generator Hi. So the first thing you want to know about quantum group, it's not a group. It's defined, an algebra defined in terms of a generator relation. The generators are known as Chevalier generators, like a semi-simple algebra, Fi, Ei, Ki. In our case, is invertible, subject to familiar relation, including the so-called quantum set relation. You start with the Cartan integer Cij. This relation looks largely familiar. And the only new thing is this square bracket. This is so-called Q binomial, replacing the usual binomial coefficient. And the index Qi is a power of Q depending on the length of the simple root alpha I. Quantum group admits a triangular decomposition. U minus is generated by the Fi, U0 is the Cartan generated by the Ki, and so on. Let me give you a quick review of the rank 1, the only rank 1 quantum group, quantum ACO2. The generator EFK, but you rather want to think K is Q to H is the algebra generator, ACO2. And then the first two relations are rather standard. The last relation, EF commutator, equal to K minus K inverse over Q minus Q inverse. You can imagine at Q equal to 1 limit, this goes back to H. And it has the similar representation theory. The AON, the simple quantum ACO2 module, has highest weight n, highest weight factor eta. It's n plus 1 dimensional. It has a basis given by highest weight factor eta. Then you repeatedly apply F. And eta is highest weight. And the weight factor if k eta, now kx by a weight q to n minus 2k. You want to think n minus 2k is the weight. Now, quantum group is a Hopf algebra. It comes with a co-multiplication delta from U to U tensor U. A key new feature about quantum group is the non-co-commutativity. That is, if you swap the image of co-multiplication, the two copy of U, it's not the same as delta itself. This is kind of symmetry breaking. Turns out this is rather the key features which makes quantum group so important, so interesting. Well, quantum group with this delta was highly contagious, spreads widely to community in math physics, quantum topology, representation theory. Sometimes a subject is too serious, you can only joke about it. So that answers what is a quantum group. That's an interesting question. Can quantum group be invented earlier? It could. Recall Iwahori constructed Heck algebra as convolution algebra on a pair flag with the diagonal action general linear group over a finite field. The cardinality is basically related to the parameter in the Heck algebra. Now you replace the flag by n-step flag. Do the same construction of convolution algebra, known as Q-Schur algebra, depending now two parameters, n and d. You take a suitable inverse limit over d, you get an algebra depending on n, that's quantum ACON. This, technical-wise, could have been done in late 1960s, but we have to wait. That was a theorem due to Beilinson, Lustig, Matheson, 1990. What is a quantum group good for? Well, helps win a Fields medal. More seriously, it has really numerous applications to very diverse areas in mathematics. I only know a little bit about representation theory, and so let me focus on this, tell you something. I made up a top 10 list, and which is personal, and different people could make up somewhat a different list. And in a different day, I could give you a different list. But anyway, R matrix was introduced by Greenfield to repair the symmetry breaking caused by this non-co-commutativity of co-multiplication. And Jingbo constructed the quantum Schur duality, and then Lustig developed this really deep theory of canonical basis. Kashiwala has another approach. Canonical basis has application to super type A Cauchy-Lewis theory for superalgebra, known as Blandung's conjecture. Ringo gave a Hall algebra realization of half quantum group, and Bridgeland generalized to the whole quantum group. In the affine type, just like in the Lie algebra, it admits a loop type of presentation due to Greenfield. Quantum group admits a braid group symmetry. That was a fundamental symmetry in the area. And geometric realization I already mentioned, but this further work connection with like Nakajima equivalence and others. The canonical basis with positivity has led to categorification due to Kofanov, Lauda, and Hukier. This is at least look long. It's only a fairly small set of people working in this area as kind of representative of some of the things I mentioned. Okay, and these are rather point of different direction under quantum group, and there are certainly several things I did not even have time to mention. These have been topics of many ICM lectures. That's all I want to say about quantum group before moving on. So, I want to add I. What is I? Who am I? Someone asked. Well, let me show you the overall picture. We already see this line, deformation of quantum group. Well, deformation is semi-simple algebra. But this is an orthogonal direction you can go. You can pass from complex to really algebra, or alternatively, symmetric pair, which is more suitable. You can work over a more general field. And these two have a common generalization known as quantum symmetric pair. U is quantum group we have been talking about. Ui is a subalgebra. I will call this an I quantum group. Let me first review quickly the classical setting of symmetric pair. And for our purpose, I prefer to focus on the complexly algebra version, not the global version. So G is semi-simple algebra. K is a fixed point subalgebra under an involution known as Cartan involution. First example, split symmetric pair. We take the Cartan involution to be also known in my area, at least Shibari involution, omega. For the classical matrix algebra, is simply minus transpose. So in this case, the fixed point subalgebra you see is generated by Fi minus Ei, as I runs over our simple root. Take G to be ACON. G omega consists of our skew symmetric matrix. So that's SON. Another example. Theta is omega above composed with a diagram involution. I allow the involution tau to be identity. So in this case, the fixed point subalgebra has this generator, which is reasonable. Again, if you look at G equal to ACON, now tau is not identity. The fixed point subalgebra is something like this, ACON over 2 plus GON over 2. And this is known as type A3 symmetric pair. Notice our choice of Cartan involution do not preserve the standard Borel. Turns out this choice is rather suitable for the Q deformation I'm going to talk about. So Cartan already classified the elusive symmetric pair, or equivalently, the real forms. There are different ways to parameterize this. My preferred way is to use the so-called Satake diagram. You start with a thinking diagram I, you give a bicolor partition, black and white, under some suitable condition. Tau is a diagram evolution you need to remember. Could be identity. And we see the notion of quasi-split. Now in terms of Satake diagram, simply correspond to this no black node in the diagram. In addition, you call it split if in addition the diagram symmetry tau you choose to be identity. Now come to the question, what is an I quantum group? You start with the quantum group U. And Gil Lester around 2000, she started with a Satake diagram and construct a so-called quantum symmetry pair. U is a quantum group U. Ui is a subalgebra. Not actually subalgebra. It has the co-ideal condition, means delta tends Ui to Ui tensor U. For Hopf algebra, it's rather too strict to consider Hopf subalgebra, not too many. And co-ideal turned out to be a fairly good replacement. And also the other requirement, you want it at Q goes to one limit to recover the enveloping algebra of symmetry pair. And this notion has been generalized to Katsumudi type. Rather, we want to talk more precisely about the so-called quasi-split type. In this case, there's no black node. And the quasi-split I quantum group is generated by this part of a katan in the quantum group, U0, fixed by the involution theta. This is less important part. The important part is generated Bi. So Bi, you see the classical case, adding F and E. This is a version of that. Okay? And this red phi sigma I is some non-zero scalar known as parameter. In the classical case, you choose -1. It turns out for different choice of parameter, these algebra are all isomorphic up to some field extension. So these parameters both irrelevant, depending on what the question you're asking, also become important. And in this talk, we restrict ourselves to only quasi-split I quantum group. It's less technical, and the parameter to be Qi to -1. A similar question before, can I quantum group be invented earlier? Might, it might. Recall Beilinson, Ludwig, Macpherson, they constructed a convolution algebra using the n-step type of A flag, whose inverse limit gives you the quantum ACLN. A natural question is, how about replace the type A by BCD? This is a problem I heard when I was a graduate student in MIT in the 1990s. I know some people have worked on that. And well, back then probably you will have some obvious answer in mind, but the spoiler, that's not right. This is not going to give you a quantum group of BCD. The answer is I quantum group of type A3. If you work hard in the 90s on the problem, get something, you may not believe in it. And this was still in our work a few years ago. We had the hindsight at that time. We knew what we were looking for. Okay. So our view of the I quantum group is a generalization of quantum group, just as a real reductive group generalized complex group. So let me explain. So you consider the diagonal symmetric pair. G delta is a diagonal copy of G cross G. You can replace in terms of Satake diagram if you wish. So this obvious quantization, the pair will be U tensor U and the red a copy of U. How you think about U as a subalgebra? Mainly, you want to think in terms of the co-multiplication. That is algebra homomorphism embedding. And with a little twist. The reason is the image of delta is not co-ideal. But no big deal. That change is small. So what is an I quantum group good for? And starting about 10 years ago, in the first paper with Huang and Bao, we advocate our fundamental construction from quantum group done in the last many years admit natural I generalization. Proof can be tricky. So what are the difficulties to make I quantum group difficult? Number one, for lack of triangular decomposition. Number two, in contrast to the quantum group, which has only one rank 1, quantum ACO2, now you have a bunch of real rank 1. Those local cases you have to understand. And another one is, for the usual quantum group, all those deep results, Lustig and others, depends on a natural integral form. And the integral form in the setting of I quantum group is far from obvious, even in split rank 1. Some of you may not be so easily convinced about this I slogan and about the importance of I quantum group. I know someone who shared the same view with you. What is another strong supporter from totally different angle? So let me tell you a few I things, and you'll be the judge if you want to believe it. We go back to the quantum group rank 2, but I want to understand its integral form. So quantum ACO2 acting on Ln. Okay? So now you want to introduce a bi-involution. On the algebra, it fixes Schur generator E, F, send K to K inverse, Q to Q inverse. If you work on representation, it fixes High-Sway factor too. This is a basis on the representation known as canonical basis. In this rank 1 case, very simple. It's simply divided power. And if round parenthesis K is defined to be F to the K over the quantum K factorial. Quantum integer defined. Lustig integral form of quantum group is a subalgebra quantum group over the range CQQ inverse, generated by this divided power. This definition for higher rank is the same. Very easy. And in this rank 1 case, it's very quick exercise to check. It preserves this integral form of the representation, Ln, the span of the divided power, canonical basis. Lustig integral form for quantum group are reflections of deep categorical and geometric structures. I want to now try the split rank 1 I quantum group. So the larger group U is UQ of ACO2. My I quantum group in this case is a polynomial algebra with a single generator. How simple can you cannot get something simpler? Well, B is given by linear combination F plus Q inverse E K inverse. This I quantum group admits a bi-involution fixing the generator B. An elementary question you want to ask, is there any I analog of this divided power sitting UI preserving the integral form? Turns out if you play around, this already leads to a totally new I phenomenon. You consider the representation Ln for uneven, and natural to replace the second divided power by replace F by B. Try this, B squared over quantum 2. And good news, this is preserved. Then you try again the next one. Turns out you need to modify something like this to work. And then you run out of luck, you try again for odd. Then you need another sequence. The second divided power, you need like B squared minus 1 over quantum 2. And then you continue, and this one will not work for uneven. Let me summarize, make a definition. I divided power. This depends on a parity. I will only give you the definition for parity even, 0. This formula looks a little involved, but actually very simple. This is a polynomial in a generator B of degree m, which can be factorized into the linear factor with all those roots being quantum even integer. And also its leading term in a suitable sense is Luttig divided power. And this is a new basis for this polynomial ring in one variable with remarkable positivity and integrality. The structure constant are polynomial with non-negative integer in QQ inverse. I want to say this is new even at Q equal 1. And because this work on the integral form, actually it's not just for the algebra symmetric pair. You can think it's work on the group level. And the consequence of this is not fully explored. Now let's continue to restrict ourselves to the Ln uneven. I sometimes switch notation to 2 lambda. You apply the I divided power to highest wave vector. You try to write this element as a linear combination Luttig basis, divided power basis. And look a little bit involved. There's 2 different cases, but if you have -1, you keep all -1 everywhere, otherwise you remove it everywhere. Okay? That's not a formula you want to remember offhand, and you rather want to remember the main feature as follows. The I divided power applied to eta can be written as Luttig divided power of the corresponding power plus lower term. The lower term with all coefficient now not in Laurent polynomial, is in polynomial of Q inverse with no constant term. The higher I divided power annihilate the highest wave vector. Therefore, the first few of them, they form a basis for the representation, and this is known as I-canonical basis. Now, if you can reread the item 1, that is an expansion formula of I-canonical basis in terms of Luttig canonical basis. It has a positive integral structure, constant. This is a reflection of a geometric categorical structure. And you can put it together to get a basis, also called I-canonical basis on the algebra level. It depends on choice of parity. To the expert who knows quantum group better, you rather want to compare this formula with canonical basis formula for the tensor product. And the similarity is simply striking. This is no coincidence because you can view this classical formula as an example of a diagonal quantum symmetry pair. All right. Now it's time to present a couple applications. I-quantum group so far has been defined as subalgebra. It's certainly natural and beneficial to have a presentation. Right. And this has been done in finite type by Gail Lester. I will just focus on, for simplicity, the split case. And the natural starting point is you start with the usual quantum set relation, Fi Fj. You reply Fi Fj by Bi Bj. Write down something. Ask yourself, is this equal to 0? Oh, probably not. Then what is equal to? Turns out, in the case of Cartan integer, Cij is -1 is not so bad, equal to Bj. When Cartan integer is -2, the formula getting a little messy. You may not remember this too quickly. When Cij equal -3, the margin here is not wide enough to write it. For Cij equal -4 and higher, back then there was no formula. And when you look at this kind of formula, you will not be blamed if you don't think this class of algebra is too interesting. Well, one need to think again. Let's go back to quantum group. This is a standard way to reformulate the quantum set relation. you can get rid of the Q binomial by using the I divided power. This reformulation really pleasant, pretty, yet alternating sign. Okay, that is again a reflection of deep homotopical structure, some complex. Anyway, we want to generalize the last formula to split a quantum group of arbitrary Kac-Moody type. Turns out the formula is extremely simple. You simply replace this quantum set relation in the I divided power form in terms of I divided power. That is a uniform formula. And the catch there is you need to read the index, the parity, a little bit careful. If you start with parity even here, when X on something passing Bj, you need to change the parity to the Cartan integer. So both parity can be involved in this formula. And other than that, this formula and this formula, they are in the same form. More importantly, this formula is in integral form, suggesting a categorification. Second application, recall Jingbo generalized the Schur duality. You start with a quantum ACON and its natural representation denoted by phi. You consider this tensor power, the quantum group X, because U is a Hopf algebra. And the symmetric group HD action can be defined to a Hecke algebra action. And Jingbo's theorem says the image of these two algebra in the endomorphism algebra, they form double centralized Baker mu. Can enhance this action from Hecke algebra type A to type B. I'm not giving you the explicit formula for this action of the actual generator. On the other hand, you can consider this quantum symmetric pair of quasi-split type A3, so you have this sub-algebra UI. Then the Schur duality simply says the following. You replace the larger quantum group by a sub-algebra, smaller, replace the Hecke algebra type A by a larger algebra, they still form double centralizer. This, you might think is rather just a curiosity. From my perspective, this is a shadow of, again, categorical and geometric construction. So that's lead to the third application. That's studied in my paper with Bao. And in that paper, we initiate the construction of the icanonial basis, generalizing lossy construction. And you start with any based U module, you construct a new basis. We already saw one example of this. I divided power is such an example. This is very flexible. In particular, you can apply to the phi tensor D. On phi tensor D, you have Lutic canonical basis, but you also have a new basis, which is our icanonical basis. And the claim is this basis and Cauchy-Riemann basis type B arising from the Hecke algebra action, they are the same. This similar type A statement, you simply use Lutic canonical basis. Okay? And Cauchy-Riemann basis size is type A. So from this perspective, you want to think phi tensor D is a shadow, or rather, more precisely, a glossary group of BGG category O. There are two versions you can think. Type A will be more classical, using Lutic canonical basis. And if you want to work with BCD, you want to use our icanonical basis with Bao. And this can be further generalized and lead to a formulation of Cauchy-Riemann theory of type BCD Lie-Super algebra using the icanonical basis on a mixed tensor. For this Lie-Super algebra, the traditional formulation Cauchy-Riemann theory breaks down because the wild group is not enough to control the linkage. And this reformulation in terms of quantum group size generalized from non-super to super, and it works. Okay. Again, in type A case, this was known as Blandon conjecture, first proved by Chen, Lan, and myself. In that setting, you use Lutic canonical basis in type A. Sorry, this slide is a little technical, even though I try. There are a bunch of, really, I should call them theorem, but I don't want to phrase that away, so, because I don't want to formulate, introduce notation and so on. The theorem involved here, in my own view, are deeper than the theorem which I showed you, but those previous theorems are easier to stay. Okay. Let me put a little remark here. So this work with Huang Chen was done in 2012-13 when Huang Chen was a graduate student. And the moral of the story to junior audience is yes, you can. This will be my last slide, but I can talk forever on this. But I can also finish in one sentence if you want. Long story short is I give you a top 10 list for quantum group before. All those items now has I generalization. Okay? And you already see a few of those, like definition, presentation, there's a bunch of other people's work. I don't have time to get into. And then the next few items we just saw is 3, 4, 5. They all come together as a package. But I did not mention the two. This quasi-K matrix and K matrix, these are generalization of gene fields R matrix. We will lead to this concept because of the need to construct I-canonical basis. Lutic uses quasi-R matrix in order to define bi-involution canonical basis on tensor product. Our construction is generalization of that. Okay. There are a few more items. This one I also commented. There was a geometric realization of I-quantum group of type A3. And this is another item. The KLR type of categorization of quantum group in one particular case had been generalized to I-quantum group. And Bridgeland hierarchical construction of the whole quantum group can be generalized to this I-quantum group setting. These are more recent work now. Okay. And there's also this gene field presentation for a affine quantum group. That is the loop algebra type of structure on the affine quantum group. Turns out it also has a I generalization as well. And these are getting more and more recent work. And this list continue to grow. And one more item here. Lutic Breed group symmetry on quantum group has an analog, what we call the relative Breed group symmetry. And this is associated to the relative wild group of the symmetry pair. Let me also quickly add, even though all those 10 items in quantum group admit generalization, these are far from being complete. Many of these items are only just get started. Okay, in our new situation, we have quite a few rank 1 case. If you pass to Kasmudi, there's even no classification of rank 1. So really depending on the question and situation, some of these work are far from being exhaustive. So I'm hopeful this list will continue to expand, both in scope and in depth. And with luck, there might be more future ICM talks on this subject. That's all I want to say. Thank you.
So thank you very much for your talk. Did you receive a question from Discord?
No, I did not. But still, if people want to, they can still send me
I may not answer in the real time, but I certainly will look again, like later tonight or tomorrow.
Okay, then I allow myself to ask one question. Well, first, I quantum group. Why I? The I.
Yes, you are not the first one who raised this question. It's started as a joke in private, talking to our collaborator, and start with notation UI is there first in paper, but then gradually all these concepts in quantum group need to be generalized. We need more and more terminology on this side, and historically people call this I-quantum group quantum symmetric pair radical ideal subalgebra. So it's a little long. More importantly, it refers to a subalgebra, so it's not independent. So this algebra UI, sometimes you want to treat independently, so you don't want to call it a subalgebra all the time. So it needs a name. But so at some point, we in our private conversation, we just start calling I-quantum group. What I stand for is everyone's guess. Yeah, different people depends on if you are Alice or if you are John, and they have different answers, I think.
Okay, thank you. And another question. You gave a top 10 list that is quite long, and you developed some part of it. Could you explain a little bit more some items from it?
Yeah, that's a great question. And again, these items, almost each item deserves a lecture on itself if I have the time. And also, let me also quickly add, that's a good question. Allow me to say something which I didn't. Like this relative breed group action was a conjecture of Kolb and Periclini around more than 10 years ago. So we were proving their conjecture. And this has application to construction of a Q root vector, and also to construct a dream field type of presentation. And the dream field type of presentation for usual quantum group was instrumental to develop the finite dimensional representation theory of a fine quantum group. We are hoping the same story, but maybe at a more challenging level, will be developed in the coming years. So they are, many of these items I listed is far from being complete. For example, the Hall algebra construction, we so far could only get it done for the quasi-split type. When the Sataki diagram has a black node, we still have difficulty. The I categorization, even this split rank one or all the split type, so far is not in the literature. But I'm hopeful this picture might change within a year, let's say. So many of these things are still really developing, and it's a little hard to predict who will get which particular item move forward and when. But I think we expect to see development every few months or something.
Thank you very much. Thank you very much for your talk.
Thank you very much.